Hello, this is Xiaoping Xiao, a professor of mechanical engineering at the University of Iowa. Today, I will present machine learning in multi-scale modeling of metal ceramic composites. So the composites we studied is spatially tailored materials in which the volume fraction continuous change in space. This material is also called a functionally graded material, and it is heterogeneous, and due to the volume fraction distribution, so we can tailor the effective material properties. And if we consider the volume fraction changes is only in one direction, so here this is the volume fraction as a function of the coordinates, for example, along the thickness of one plate. And N is the model parameter to control how the volume fraction, the distribution looks like. Could it be linear, could it be nonlinear. In two-dimensional case, and the volume fraction will depending on the x and the y coordinates in 2D case. And eta x, eta y, nx, ny, they are the control parameters to control the volume fraction distribution. So in this case, we consider the titanium dibride composites. Titanium is a metal and titanium dibride is ceramic. So this is metal ceramic composites we consider. And for the titanium and titanium dibride, so we have the material properties listed in the table. The multi-scale approach we used in this study is from microscale to macroscale. We use finite element paradynamics as the simulation tools. And we first do the microscale simulations to collect the data. So once we have the data set, we use machine learning model to do the regression and the classification. For the regression, we predict the material properties. For the classification, we can classify the material is failure or non-failure, giving the deformation. And the machine learning models could be deterministic and probabilistic. We first use finite element method to do the simulation at the microscale. And here we consider the microstructure uncertainty that include the size of the particle, orientation of the particle, and also the size, orientation, and the geometry of the particle. So those are the uncertainty in the microstructure. So giving a particular ceramic volume fraction, so we can generate the different micro scale configuration. So then we do the simulation. So here it shows at the 20% ceramic volume fraction and the microstructure different, the simulation configuration different, and the results are different. And since we use finite element method, and after we generate the microscale configuration, we have to do the meshing. And however, it is difficult in meshing for the ceramic volume fraction close to 50%. So therefore, in our simulation, we only do the simulation for the ceramic volume fraction from 0 to 25%, and then from 75% to 100%. So after we collect the data and we do the data analysis using the supported vector machines to generate the regression model to predict the Young's modulus and the Poisson ratio, and compare with the test data as well as some theoretical analysis. So here we can tell actually the Young's modulus Poisson ratio, they don't have much uncertainty here due to the in data set. But however, and then when we study the tensile strength, actually tensile strength has pretty high uncertainty. And also, if we go back to look at the original simulation results, and even at the same volume fraction, and the material fails at the different strength because of the different micro scale configuration. So therefore, based on the collected data, we can have this binary map and at a particular strain and giving the ceramic volume fraction. And from the data, we can calculate the failure probability. We can calculate failure probability. And here, non-failure, 100% non-failure, 100% failure. But however, there's no clear interface. Around the interface, there's a gray area, and that means that the failure probability actually is between 0 and 100%. That's the because of the microstructure uncertainty. So with such data, and we can train a artificial neural network as a classification model. And this is what I trained for the classification model. And although the training data we have, it's only for the volume fraction from 0 to 25%, and then 75% to 100%. But with the AM model, we can predict the failure probability for the volume fraction between 25% to 75%. When we also do the another testing for such a classification model, so at two different ceramic volume fraction, 10% and 20%. So we did actual 100% simulation. For each simulation, based on the simulation data, we can calculate the failure probability depending on the string, and then we compare with the prediction. So they are in a pretty good agreement. So after we train the model and we pass the regression model and the classification model to the macroscale simulation. So in the macroscale simulation, we did the simulate the plate, square plate with different ceramic volume fraction distribution, and there's a hole at the center of the plate. And here we can, under the uniaxial tension, so we can look at the failure probability profile, and for on the plate with the different volume fraction distribution. So mostly the failure actually can be viewed as the crack propagation and towards to the smaller ceramic volume fraction. So as I mentioned, when we use finite element simulation, it is difficult to do the simulation at the macro scale when the ceramic volume fraction is between 25% to 75% because it's hard to mesh. So therefore here we use paradynamics. So we use paradynamics to redo the study. So paradynamics for the in the Goblin equation instead of derivatives, and here we use the integral term. So here we use a bound-based paradynamics. So the pairwise force has two terms. One is relative to the bound stretching. Another one is relative to the bound rotation. And the first and the second macromodulars, depending on can be calculated from the material properties. And also the critical stress can be calculated from the strength. And to generate the microscale configuration using the paradynamics, it would be easier than the finite element because there is no meshing needed. And at the microscale, so for the paradynamics, so we have a group of particles. So we just randomly assign the particles as either metal or ceramic. And also here, we introduce 1% to 2% vacancy into the microscale configuration. So here, this is the three configurations at the different ceramic volume fraction. And of course, at each volume fraction, we generate the different configurations to do the simulation and collect the data. So after we collect the data and we do the machine learning model training again. So here, instead of deterministic machine learning model, we use a Gaussian process regression, which is a probabilistic machine learning algorithm. And in this probabilistic machine learning algorithm, the model parameters that random variable, and the mean value standard deviation for this random variable can be obtained from the training data. So after the random variable, the model parameters that determined as a random variable, so then the prediction would be the random variable as well. So we use Gaussian process regression to predict the failure strength Young's modulus and the Poisson ratio, and here plot the 95 confidence interval compared with the test data. So after we have this machine learning models, we can pass the microscale paradigmatic simulation. So the first simulation, we do the spallation. And here we consider the plate, the thin plate, and the volume fraction changes along the thickness. So the volume fraction changes only along the one dimension. So for the plate, and one surface is applied a force. Such a force would be the due to the explosion. So there's a sudden force applied on the one surface. Another surface is a free surface. So therefore, after load is applied, so there is that's the explosion applied on one surface. So therefore, there is a compressive wave propagated along the thickness of the plate. So after reach to the free surface, it's reflected as a tensor wave. Once the magnitude of the tensor wave reach to the fatal strength, so there is a fracture occurs. So we have a spall, we have a spall thickness, and the spall speed. So we did a study. We first study since the volume fraction changes from along the thickness. So from 0% to 100%. So one surface actually is metal, another surface is a ceramic. So then gradually changed from metal to the ceramic along the thickness because the volume fraction is changing. So here we studied the exposure force applied on the metal surface, and then the spallation will occurs close to the ceramic surface. So we can tell actually how this ceramic volume fraction distributed will have the significant impact on the spall speed and the spall thickness. And here N is control the ceramic volume fraction distribution. So also we studied what if the explosion occurs on the ceramic surface, and then the free surface will have the spallation. And from our simulation results, and we conclude actually the volume fraction distribution actually has no significant impact on the spallation if the explosion occurs on the ceramic surface. So this is the if the volume fraction distribution is along the one-dimensional. So for the two-dimensional case, again, the plates, two-dimensional plates, and with a central hole, and we consider the uniaxial tension, and the volume fraction distribution is two-dimensional, and with 4 different distribution. So we have plates A to B, A, B, C, D. And for those 4 different states, and the volume fraction is different, and the total ceramic volume fraction, they are different as well. And after we do the simulation, we find that the fracture or the crack initiate, of course, from the hole and will towards to the smaller volume fraction location. And of course, mainly because of the different total ceramic volume fraction, the mean value and the standard deviation of the fatal stress are different. And we also look at the stress strain curve for different plates, and of course, because of the different distribution and the fatal stress, fatal strain, they are different. And looks like the smaller for the plate with smaller fatal strain, they have a higher fatal stress. Okay, so in this study, we use both finite element and paradigmatics to do the simulation, generate the data at the micro scale, and consider the microstructure uncertainty. And then we pass, we train the machine learning model, pass the model to the macro scale simulation for the large scale simulation. And currently, we're working on the titanium boron composites, and we have finished quantum mechanics and the molecular dynamics study on the interface between the titanium boron. So now we are also waiting for the experimental validation and then do the simulation at the micro scale for the to validate the multiscale model. So we would thank the support from the ASF and Department of Education. Thank you.